Let's do this. Encryption. So last time we introduced what encryption is. We talked about RSA and how it's the magic of mathematics that makes encryption work. We got to the last slide, which said encryption demo. So I want to do that demo, and then we'll get into today's slides. So I have some Python code here. And before I get this question, you won't have to do this at all. This is just for a demonstration. You won't have to write code that looks like this in your homework or your project. But this is code that's going to encrypt and decrypt a message. For this, I'm using the crypto library. I say the crypto library, but it's in my requirements. It's this PyCryptodome, because, oh, never mind. But I'm going to generate my keys. I'm going to generate 2K keys, so pretty large keys we use for encryption. 2K is about the minimum that we want to use to say that we're pretty secure, which is a lot of entropy. But we want to really make sure we're secure when it comes to encryption. Generate my keys using the crypto library, and then I'm going to generate a cipher, which is going to use a padding scheme to be able to do my encryption in a secure way. Encrypt, I'm pretty much just calling the encrypt method. Decrypt, I'm calling the decrypt method on that cipher. And I'm making sure my encodings are right. This does want base64 encoding, so I can get some pretty, or actually I want base64 encoding so I can get some pretty stuff and not just bytes printed to the screen. So that's why I'm using base64 here. And then decoding, making sure all my types match up. I'm going to encrypt the message hello, and I'm going to encrypt it twice using the same exact cipher, using the same exact keys, the same exact public key to encrypt. I'm going to print out both ciphertexts, and then I'm going to decrypt both ciphertexts, ciphertext 1 and 2, make sure I got my 1s and 2s in the right way, don't have any copy and paste errors. I'm going to decrypt them both with the same cipher, with the same private key, and then print out the decrypted text. And the big thing I want to point out here is how the padding algorithm works. When I print all this to the screen, I see my two ciphertexts here. Here's my first ciphertext, a big, long, random mess of garbage. And my second ciphertext, a big, long, random mess of garbage. The important thing here is that these two crypto texts are completely different. And this is our padding algorithm at work. This is what's giving us security, even though I have a very small message, just 5 lowercase characters, very low entropy message, but I get completely different crypto text, which for all intents and purposes cannot be broken. Nobody's going to read what these say unless, obviously you all know what they say. But without the private key, if somebody just has this and my public key, they cannot crack this. They cannot crack this. With hashes, we saw that there's a multitude of attacks. We did a brute force attack in lecture. I think I even used hello, or we used some 5-character word at least. And we cracked that hash. And then we talked about dictionary attacks and how dictionary attacks are much more effective at cracking hashes when they are hashed passwords specifically. But nobody's cracking this. You're not cracking this. Encryption is extremely high entropy without breaking the crypto system itself, without completely blowing the underlying mathematics wide open and changing the world forever. They're not breaking this. It's not happening. But even though these crypto texts are extremely different, as long as we have the private key, both these crypto texts decrypt to the same message. So even very low entropy messages have very high entropy crypto texts. This is a very nice feature that we get from our padding algorithms and something that makes cryptography realistically usable at all. It wouldn't be much usable without these padding algorithms or some other solution for the same problem. Encryption without padding algorithms, you got problems. Always use padding algorithms. If you're building your own crypto system, which in general just don't do that. You use a library, use some tried and true method. There's so many things in cryptography, so many vulnerabilities that have been exploited and then patched by the major libraries, the major players. Use what they've done. Don't try to build your own. Don't use code like I just showed you. I wouldn't use that in an actual setting that needs to be secure. It gets wild. Just for a taste, it gets wild what they do. Just measuring the time that your encryption takes can give attackers some information about what you're encrypting. And then they have broken some crypto systems just by looking at the timing. So libraries will add a random delay in the encryption process to make sure that people can't use that information to figure out what you're encrypting and figure out what's going on with that thing. There's so many attacks and so many really, really, really clever ways. Hi, Tomato. That gets scary. Just use what's out there. Use the tried and true methods. Okay, HTTP over SSL/TLS. Let's talk about it. Let's start with signs. Any questions before we get into today's content, by the way? Signed certificates. So we have a big vulnerability with everything we talked about last time, a big problem with the way we set that up. That needs to be addressed or else we're not secure. So we want an HTTPS connection. That's our ultimate goal. We'll get there by the end of today's lecture, at least theoretical, and then on Friday we'll do it in reality. We want an HTTPS connection, an encrypted connection. The very first thing that we have to do, so we have the server, it's going to generate their public-private key pair using everything we talked about last time. The first thing we have to do is the client's going to say, hey, server, what's your public key? This can be intercepted. The man-in-the-middle attack is what the name implies. There's somebody in the middle of that connection who intercepts that request. When I say, what's your public key? They intercept that. That message never makes it to the server. The attacker responds with, here's my public key. You happily encrypt the message, send it to who you think is the server, but you send it to the attacker who's intercepting the message. They have the private key because they sent you their public key. So they decrypt your message. They can see everything that you just said. And they can read that message, generate a response, and send a response back to you. And usually they don't have to do that because the first thing that you're going to send them is, here's my username and password. They decrypt it. You're compromised. Then after that, they can stop their attack. You say, oh man, this page is broken. You hit refresh, then it works. They let that go right to the server, and you have no idea that you just sent your username and password to an attacker. Because the domain name is, the actual domain name. You would have no idea that something went wrong here. So we need to address this. If this were not addressed, this attack would be happening all the time. The attackers would have these deployed all over the place for any major site, and we'd all be really screwed. So when we get this, and this is the vulnerability right here, when we get this public key, how do we know we got the real public key for that server? This is what we want to solve. This is the point of attack that we're going to patch, and we're going to do that with certificate authorities. Certificate authorities are going to make sure that we get the right certificate, that we actually get the certificate for that server. So a certificate authority is a trusted source with a public key that everybody knows. They have their public key. They share that public key with us. Everybody has the public keys for a certificate authority, or at least what we'll eventually know as root certificate authorities. And we have those pre-installed on our machine. These certificate authority public keys are coming from either our OS or our browser. A lot of them are installed by our operating system. That sentence came out wrong. We have a lot of certificate authority public keys installed by our operating system, and most browsers, including every Chromium browser, is going to use those certificate authorities as their trusted certificate authorities. Firefox is one that will come with their own pre-installed certs. And I was trying to not introduce the word cert yet, but with their own pre-installed public keys of their own trusted CAs, and use those ones. So it's your browser or your OS, depending on specific circumstances, whatever your software you're using. And we're going to assume that went well. So we're going to assume there's no man-in-the-middle attack during the installation of these certificate authority public keys. Which is maybe a strong assumption, maybe not, I don't know. But there is actually The whole world of security, at least online security, all of it has to start with an assumption somewhere. There actually is no security at all online. We need to start with an assumption somewhere. And for internet traffic, this is where our assumption comes from. We're going to assume that when we installed our operating system or when we installed Firefox, that we actually did get a proper installation and that those keys are the actual valid keys for these root certificate authorities. As long as that assumption is true, then everything else builds on top of that. Everything spreads and builds the internet that we want. But if anything's compromised with those public keys, then we're in trouble. And that's happened with some lesser-known certificate authorities. I'm not aware of any major players being hit, but some lesser-known ones have been compromised, and attackers were able to get their public keys installed as a certificate authority on trusted, devices as trusted certificates, and that's obviously bad. Those attacks are short-lived, thankfully, but it does happen every once in a while. So that's our root assumption for all encryption online, all privacy, everything that's encrypted online. That's our assumption. So you installed your operating system properly, or that it was installed properly, that nobody compromised that process. And these certificate authorities are going to issue certificates which are verified public keys to domains and subdomains. So if you have a domain, like I have CSE312.com, I'm going to go to a certificate authority and say, hey, can you sign my public key? And they're going to sign that public key, issue me what's called a certificate, and then that certificate is going to be my public key, but in a verified way. That came out wrong. I'll just wait till I get to the slide on that one. But what I need to send to the certificate authority is I have to verify that I do control that domain name. So I can't get a certificate for, say, google.com. I can't get my public key signed for a valid google.com certificate. I have to prove that I control that domain name, which is easier than it sounds, surprisingly. And then send them my public key that's signed with my private key. So I'm going to send them my public key. They're going to verify through the signature that I do actually own the private key. So I can't just send any public key. They're going to verify that I sent the right one. And then they're going to send me a certificate, which is my public key. That's really what we want. The certificate is going to be the public key. It's going to contain it at least. The domain name that public key is verified for, the name of the CA that signed this certificate, and then the signature of that CA. They're going to have a cryptographic signature of a hash of the certificate. So they take all the content of the certificate, which is public knowledge, they're going to hash it, and then they're going to cryptographically sign that hash with their private key. The CA private key, which is a value which must be kept secret, absolutely must be kept secret, or else a lot of things break. They're going to sign it with their private key, and then that signature is used to verify my public key. So when somebody visits my site, so when somebody visits your server, you're not just going to send them your public key and say, here's my public key, use this if you want to encrypt anything and send it to me. Instead, you're going to send your certificate. That user gets your certificate, which contains your public key, the domain name, and the CA name all in plain text. The user is going to look up that CA, look up their public key, which might be pre-installed on their device, get their public key, take a hash of the certificate content, and then verify this signature with their public key. So verify the signature with the public key and make sure that when they decrypt this signature, that hash equals the hash that they computed of the hash of the body. So this is what we want to do to verify, and then once we go through that process and everything checks out, the user knows that they actually have your actual public key. And this is something that the man in the middle is not going to be able to fake, because they would need the CA's private key in order to spoof one of these certificates. And we trust these CAs to keep their private keys private, or else everything breaks. You go over again how they verify your signature with your private key. So you're sending them your public key, so they have your public key, and then you sign this with your private key, and that's going to verify to them that this is actually your public key. So if this signature is verified, then they know that you do control, that you own, you're verifying that you own the private key. You don't want to send your private key to the CA because it's private. You don't want to share with anybody at all. I mean, how would you even send it to the certificate authority? I guess you could encrypt with their public key. You know, I guess you could. But we don't want to send that anywhere. We don't want to take a risk. That private key stays private, stays local. But the certificate authority wants to make sure that we do actually own the private key of this public key. So we're verifying that by signing the public key. We're sending a signature of that message to say, hey, look, I do own the private key. And now with this certificate, you go to a website, you've probably heard of certificates before. So this is how they work. You go to a website, you get the certificate, you verify the certificate with a trusted CA, and then you have their public key, and now we can start the encryption process with a verified certificate, a verified public key that a man-in-the-middle attack could not have faked. And we usually don't have what we call root CAs. So there's CAs and there are root CAs. Root CAs are the ones that are installed on our machine, and there's not many of them. You can view your keychain on your browser or on your device. There's like, I want to say 50, 60-ish of them total of trusted root certificate authorities that are pre-installed on all our devices. We all have the same public keys installed on our devices, and that's the start of encryption on the internet. They don't usually sign certificates for domain names. What they do is sign certificates for other certificate authorities, which creates something called a keychain. I just used the word keychain in the wrong context there. But I meant to say cert store, I think is the correct term there. We have a cert store of like 50 to 60 certs on our devices. But a keychain is going to be a series of verifications that leads to a root CA. If I have my cert signed by Let's Encrypt, which if you look at the certificate for CSE 312, it's signed by Let's Encrypt. If I look at that certificate, it's signed by Let's Encrypt, which is not a root CA. That is not a trusted CA that your device, that your browser or your OS is going to trust. But Let's Encrypt's public key is also a certificate, and that certificate is signed by the DST root CA, which is pre-installed on all of our devices and can be verified. So when a certificate has to be verified, it's going to verify the whole chain of certificates, which could be pretty long. This one's only 3 certificates long. There's only one intermediate step. But that chain can be, as long as it has to be. And as long as that chain ends, every step verifies, every certificate is valid and does check out to be verified by the next step in the chain. And as long as that chain ends in a root CA that's installed on your device, then that's a valid keychain. And we say that this is a valid certificate, and you get the lock in your browser. Everything looks good. The browser doesn't give any security warnings or anything, unless there's something else going on wrong. That's a valid signed certificate. If that keychain does not end in a root CA, it's called a self-signed cert, and it should not be trusted. If you go to a site and it says, this site has a self-signed cert, that means their keychain did not end in a root CA, or possibly there is no keychain, it's just one cert that's signed by themselves, and it should not be trusted. You'll get all kinds of security warnings. You'll have to click proceed anyway to be able to get to the site, and it's probably a site you should just turn away from, or at the very least, if you get to one of those sites, don't put any personal information in there. Do not put any personal information, because you can't trust what's on the other end. There's one exception to that we'll talk about. It's when it's your own server and you signed the cert. Then we will use self-signed certs for that. So for your project, you need a valid signed certificate. On Friday, we'll go over demos, how to actually do that. Friday is going to be the practical, just demo day, the whole day. For your project, you need a valid signed certificate. There shouldn't be any warnings in the browser. We should go to your site using HTTPS at your domain name, and the browser should have the lock, and everything should just look great and fine. No security warnings to accept. A self-signed cert means we didn't get to a root certificate, a root CA, and this is what we'll do for the homework. So project versus homework, two very different things in this case. Project, you're going to be deployed, add a domain name, and you're going to get a cert for that domain name, which is a lot easier than it sounds, by the way. If you're scared of that, don't be. It's silly easy these days. You install something called certbot, and you do certbot.doitforme, and it just does everything for you. But on the homework, we're not going to do that because we can't do that. I would like to do it with the homework, but it's not gonna work because no CA is going to sign a cert for localhost. Just not going to happen. They don't do it. You need a domain name. You prove that you control that domain name, and then you get a certificate signed for that domain name and that domain name only. Nobody's going to sign a cert for localhost. It doesn't even make sense to do that. So for the homework, since we're testing on localhost, we're going to use self-signed certs. You should only use this for development and educational purposes, but never use a self-signed cert in a deployment to actual live users, and don't use a site using a self-signed cert, especially if you're giving it private information. If it's just a content-only site, you're only consuming their content, fine. But if you're sending any private information to them, don't. Run away from that site. At the very least, like maybe, okay, what's the worst that can happen? I would be worried because whoever's programming on the other end clearly doesn't know what they're doing, and I don't trust that they'll protect my information in any way if they're using a self-signed cert. They're probably not storing my password in a secure way. They're probably doing other things bad. So I would just run away. Let them get their cert figured out and then go back. So don't use these in practice because since they can't be verified by root CA, how do you know you didn't get man in the middle? You don't know. There could be you could be communicating with a hacker and not even know it because the domain name in your URL is still going to be valid when there's a man in the middle attack. You don't know that that's happening. To generate self-signed certs, we're going to use a library called OpenSSL. I suppose you don't have to, now that I think about it. If you want to generate your self-signed certs in a different way, go for it. This is the easiest way, I believe. Maybe there's an easier way out there, I don't know. But I would do it this way because it's actually not hard. OpenSSL, this is a very common library. If you found another solution to generate your certs, that solution is probably using the OpenSSL library. This library is most famous, it was a long time ago now, but for the Heartbleed vulnerability, that was actually this library. They patched it, and we still all happily use it. It's the foundation of a lot of encryption on the internet and otherwise. But that's kind of its claim to fame. That's got to be like 5 years ago, at least by now. But and there are wrappers in most languages. We're going to go right to the command line, at least in what I show you in lecture. So we're not going to worry about the wrapper libraries. And this can be used for many things, including all the things that we're interested in. And to use this command line, you have to install it first. Windows users, you actually have to install it because Windows doesn't like to make anything easier for developers. But if you're not on Windows, if you're on Unix-based like Mac or Linux, this should be pre-installed for you in probably any distro. But Windows, you have to install OpenSSL. But once it's installed, go to the command line and run this command. I made this pretty easy. Maybe I should make this objective harder. I don't know. But I don't know how to without making it. It's either trivial or impossible, and I lean to the side of trivial right now. But you can cut and paste this right from the slide, punch this in command line, and it will generate your self-signed certificate and your private key for you. You'll be asked a lot of questions when this runs. When you run this command, it'll ask you, I don't know, I say a lot, but like, I don't know, 7, 8 questions, something around there. Most of these you can just leave blank. You can just hit enter and just use the default option, which is blank for all these questions. There's one question that is required that'll cause you a lot of debugging time, but it cost me a lot of debugging time, so now I can share it with you, and now it won't cost you a lot of debugging time. The country is not optional. You must enter a country code or else everything just breaks. So country code, for example, US, I don't think anything breaks if you use a different country code, if you want to use your home country code. But country code is a 2-character code. So enter that country code. Everything else you can leave blank. let's go over this. I don't want to just give you this command and not explain it all. So let's go through each one of these flags and talk about what this is doing. First, OpenSSL, invoke the program. And then the rec, this is to request a signed certificate, which takes the parameter X509, which is the standard format for certificates, bless you, certificates that we use in the browser that we use online. So give me an X509 certificate. I want to use the RSA. I want to generate new keys, not use existing one. Give me the RSA algorithm and a 4K key. Save my private key in a file named private.key. I want my cert, my public key that's included in the cert, in a file named cert.pem. So I'm going to create two separate files when I run this command that'll be in the directory where I ran the command from. I'll have these two files created for me containing the information that we're really concerned about. The cert will expire in 1 year, and don't use a password. This is no DES. For a while, I thought it was nodes. No DES. Don't use anything. Don't use a password protection on the private key. If you have password protection, every time you use that private key, it'll ask you for your password. Not really what we want when we deploy this on a website, because nobody's there at the server to punch in the password every time someone visits your site. Not what we want. So that's this command. If you want to change any parameters, go for it, but there's really no reason. There's really no reason for you to do that if you're just trying to get through the homework. But if you're trying to experiment with things outside of the homework, that's what those parameters do. Change them at your will. All right. But actually, you won't be doing that anyway in practice because you'll be getting signed certificates in practice. There's no reason to generate your own self-signed cert unless you have to do it for homework. All right. And that's what we'll use. That's our certificate. And that's what we'll use to enable what we call TLS. And you can go into your server code and add these certs, add the cert in the private key, tell your code to use those and use TLS. But we're not going to do that. We're going to prefer a different way. We're going to use what's called the reverse proxy, which is a topic for Friday. We're going to install those certs on Nginx. And the end result is we're going to end up with encrypted traffic without changing one character of code on our servers. So your server.py, all of your helper methods, helper classes, none of that changes. All of that still speaks HTTP. And then we're going to add a layer in front of it that's going to speak HTTPS. It's going to talk to the outside world with encrypted traffic. And then when it talks to our server, it's going to say, hey, we got this request. It's going to talk using HTTP. Our server is going to respond with HTTP. It's going to encrypt and then send the response back to the user encrypted over there. This is one really nice aspect of HTTPS is it's just HTTP with a layer of security in front of it. So we don't have to change the way we code. We can still just think about what our app is supposed to do and then separate the security into another module and have that handle all of our encryption. Very convenient for us. Yep.
Is there any kind of app that could get your information between communicating with the server and the reverse proxy server?
Not really. Yes, but that reverse proxy is going to be at the very least in the same server room. And if somebody has that kind of access, you're screwed. You're already done. So even internal to a network like UB's network, we're usually confident in HTTP communicating. Maybe that's too strong of a statement. If it's not going through Wi-Fi, I mean by that one, by the way. We're usually comfortable with that, especially when, like, I'll have servers talking to other servers pretty regularly, but they'll be in the same server room. I guess I already said that. If they're in the same server room, HTTP. There's no reason to encrypt. So what does DES stand for in no DES? D. I don't know the D. It's encryption standard. And I'm not 100% why that's being used. I was wondering that when I was reviewing my slides today, like why DES would even be used for the password, but it should be D encryption standard. I don't know. The host. It would be on you. It'll depend on the organization, but it'll depend on the organization, not the client. Depending on the organization, it's the responsibility of DevOps. Depending on the organization, there may or may not be a DevOps team, and if there's not, it just falls on whoever takes up that role, but definitely not the client. No, in fact, it's pretty standard to have them expire pretty regularly now. Like a month or two, I think, is kind of the common standard now, that they expire pretty often these days. But you'll get a new cert. Like whenever a client goes to your website, they're going to ask for your cert, and you'll give them the latest one. But you have to make sure it's updated. You got to get a new cert before it goes out of date, and usually that's all automated. Like for all my sites, it's automated. I don't even know when they expire. They just auto-renew. All right, HTTPS. So HTTPS, commonly called HTTP secure or secure HTTP, even though that's kind of wrong. But if it's HTTPS, of course we're going to call it HTTP secure. Like the S stands for secure. So it makes sense. I don't care if anybody calls it that, but it is technically wrong. It's I don't even have it on the slide, but it's how do I not have it on the slide? Anyway, but it's HTTP over TLS is what it actually is what it's actually called. I already covered that. That should be the second bullet point. That tripped me up. But anyway, so HTTP over TLS, that means everything's encrypted using TLS. And there's a naming thing here. The naming gets a little weird because of this fact right here. It was the Secure Socket Layer Library, SSL. This is what we used to say, and kind of rolls off the tongue pretty good. I guess TLS does too. But it was renamed after SSL 3.0 was renamed to TLS. So if you hear SSL or TLS, it's referring to the same thing. From here on out, I'm only going to use TLS because that's what it's called these days. But SSL does stick around. We use OpenSSL. They did not rename the library. Library is still called OpenSSL, not OpenTLS, because they just didn't rename the library when they renamed the protocol. But OpenSSL does TLS these days. It does do TLS. It is a modern library. They just didn't change the name. So just keep that in mind. If you ever hear SSL, they're probably talking about TLS. No browser is going to respect SSL these days. They're just not going to, because TLS is the current standard. So TLS, the reason why this doesn't affect our server code at all is that it fits right in our network stack. It fits right in between TCP and HTTP and adds its own layer of headers, its own stuff here, but it's right after the TCP. So TCP is going to do its thing, IP is going to do its thing. We're going to get a whole message, with sequence numbers, all that. We get an entire message on our server. That message is going to be an encrypted HTTP message. TLS is going to decrypt it. And then by the time it gets to our code, unless you want to do your own TLS stuff, which isn't that bad, you just add it in your TCP code. So right before you start your server, you say, hey, TCP, I'm using TLS. Here's my cert, here's my private key. Can you encrypt and decrypt everything? And then it'll happily do that. And then by the time it gets to your handle method, everything's decrypted, and you do the same thing there. So we can handle it in our code, that's fine, but we usually don't want to. We want to write one server that can be used in any context. We just don't want to. But anyway, so TLS is going to decrypt and then hand it off to our HTTP server. And then our HTTP server is just getting HTTP requests like we have all along. No difference in the protocol at that point. HTTPS really isn't its own protocol. It's HTTP over TLS. TLS decrypts before we do any HTTP stuff at all. So there's nothing in our HTTP requests that cares that it ever was encrypted or that our responses will be encrypted. Doesn't care at all. Our code is exactly the same as it always has been. Just whenever our responses are shipped and before our requests are read by us, it happened to be encrypted on the other end before it went off to the internet. That's the only difference. It's a whole separate layer in the network stack, though. That's why I think it's more accurate. The accuracy does matter a little bit. It's not HTTP secure. It's HTTP. Oh, yeah, and by the way, we're using TLS on the other end. So no changes to our server code at all. We reuse everything we've done all semester. Homeworks 1 through 3, all that code is reused. We don't throw anything away because we're switching to HTTPS. Okay, so let's talk about TLS. That's HTTPS, just HTTP with TLS. So what the hell is TLS? Let's talk about it. Okay, so what we want, what's the problem we're facing right now? What we want is two-way encrypted traffic, and what we have is a server with a public-private key pair, and the public key is verified by the certificate authority. So what we have versus what we want is pretty asymmetrical here. We got some work to do at this point. So if the client wants to send a message to the server, okay, we talked about this. Take the public key that's verified with the certificate, encrypt with the public key, ship that to the server. It's encrypted. Server has the private key. They can decrypt and read the message. Everything's secure. Everything's verified by a root CA. Everything's good. How's the server going to send my response? How does the server encrypt a response and send it back to the client? That's a bit trickier. So what the client could do, every internet user on the planet could do, is generate their own public-private key pair, get their public key signed by a CA, send their public key to the server, server verifies it with the CA, and then uses that to encrypt and sends messages to us. We could do that. We don't, but we could. I mean, it's a solution. It's not the solution we're going to use. Instead, we're going to use a TLS handshake and do all the TLS goodness that is involved. So with this handshake, a TLS handshake, we're going to agree on a symmetric encryption key. So we're going to introduce symmetric encryption. So far, we've talked about public key encryption, where we have a public-private key pair. Symmetric encryption, you use the same key for encrypting and decrypting. So we want one symmetric key. Our goal is to get one symmetric key that the server and client both agree upon, and then they both use that same key to encrypt and decrypt. That's what we're going to do. That's what does actually happen in practice. So that's our goal. How do we agree on this key? Knowing that there can be man-in-the-middle attacks, there can be eavesdroppers, there can be a lot of things going on here that that's not trusted. Anything that goes over the internet should not be trusted. You don't know who's in the middle there, who's on the internet, either spying, sniffing the packets out of the air, or launching a man-in-the-middle attack. We don't know. So how do we do this? How do we agree on a symmetric key in a secure way? And for that, there are multiple solutions to this. The one I'm going to show is the Diffie-Hellman key exchange. And the way this works, I'm just going to jump into the math here. We're going to agree on some prime number P and some group generator G. A group generator, for those of you who haven't taken abstract algebra, which is probably all of you. I assume nobody took abstract algebra in this room. Maybe one or two of you, but anyway, it's super fun. If you're into cryptography, you should take abstract algebra. By the way, it comes up surprisingly often, including right here. That we're going to have some generator G that generates the prime group P, which means that for each value I from 1 to P minus 1, G to the I mod P is a unique value. That means G generates the group P. So if I take G and keep multiplying it by itself, P times mod P, I'm going to get every value from 1 to P minus 1. So this generates the group G. G uses the full potential of these values from 1 to P minus 1, which is a property we want in this case. Both P and G are public. These can be shared with anybody on the planet. So while we're negotiating, like, hey, what should we use for P and G, that can be sent unencrypted. And by the way, we haven't agreed on any symmetric encryption key. We haven't agreed on an encryption key yet. So this has to be sent over the air unencrypted, because that's our goal, is to set up encryption. So setting up encryption has to be negotiated unencrypted. So these are both public. We can just share those out in the open. And then client and server are going to both generate a random number. We're going to call the client's number A and the server's number B. And these are super duper private, which means that the server can't even know the client's secret number, and the client can't even know the server's private number. So nobody can know these numbers. Client is the only one who ever knows A. Server is the only one who ever knows B, which is convenient, which is what we want, because these numbers that means we can never send these numbers over the internet. Let me reword that. We never have to send these numbers over the internet, which is the only way we can really keep them private. So it's kind of a necessity of a key exchange that we have some values that aren't even shared with each other. So these are super private values. Nobody can know them except whoever generated them. The client and server are both going to compute these very specific values. Client is going to compute G, our generator, raised to the A mod P. This is why it's important that G is a generator of the group P, is that we want unique values here. We want to get the full potential out of P. P is going to be a large number. We want to make sure we really fill up that potential instead of having G like flip between two values. That's not going to be useful here. We want the full potential. G to the A mod P, and send this value to the server. Server is going to do the opposite, G to the B mod P, and send that to the client. The server is going to get this value and raise it to the power of B mod P, and the client's going to get the value from the server and raise it to the power of A mod P. So now what we have is this shared secret, G to the AB mod P. We didn't share A and B with each other or anyone else. The only thing that went over the air was G to the A mod P and G to the B mod P. Those are the only things that went over the air that contained any private information. Is there a reason for changing the cert frequently? Paranoia. If a private key is compromised, but you're changing the cert frequently, there's a limited window for the attacker to take advantage of that compromised private key. So paranoia mostly. And that's an answer, tomato. So now we have a shared secret, G to the AB mod P, and this is what we can use to generate our symmetric encryption key, or just use this directly as the key if we don't feel like taking another step. It's the choice of the client and server. And the only things that went over the air were these values. So, well, we can compute A, we can compute G if we're eavesdropping on this stuff, but guess what? That's discrete log, baby. We just talked about this last time. That's a cryptographic primitive. So for them to break this, to compute A or B, they have to break a cryptographic primitive. That's what we call secure, at least for our purposes. We hope it's actually secure, but that's secure. We're comfortable with that being called secure for encryption. So we agreed on a symmetric key, and the only time we sent secret information, to get that secret information, you had to break a cryptographic primitive. So this is secure. This is good. We accomplished our goal. We did what we needed to do. Still a few problems here, so let's talk about them. We're not talking about problems yet. To encrypt using the shared key, we're going to use something called AES, Advanced Encryption Standard. didn't remember this one either, but I put it on the slide. This actually replaced DES. I still forget what the D stood for. D advanced, maybe? But AES is a symmetric encryption scheme, which is going to work by repeatedly scrambling bytes and XORing them with bits that were generated by the encryption key, and does this over and over. This does not reduce to a cryptographic primitive, but we think it's secure. Like we're okay using it. There are theoretical attacks out there, but no known practical attacks that breaks AES, so we're still comfortable using it out there in the real world. But it does not reduce to a cryptographic primitive, so there's no math that says it's secure, but it's secure. It's secure. Trust us. Oh, and we're a little low on time, but the key here is XOR. What's XOR? Fast. Very fast. AES is fast for encryption. It's bitwise operators. Our CPU can do this directly. We don't have to have complex things that we're asking the CPU to do, like exponentiation modulo a prime, or n's not a prime, but modulo a large number. We don't have to do that like public key encryption does with RSA. AES, very, very fast. That's why we like AES here. So our TLS handshake is a client hello, which says, here are the algorithms I support. The server hello, which responds to the client hello and says, here's the algorithms we're going to use. So they take the algorithms the client supports, picks their favorite runs. If it doesn't like any of them, it might respond with, this ain't happening. But the client server hello is, here's what we're going to use for this, this connection. Server is also going to send its certificate that can be verified by the client, will be verified by the client. And when the server sends its portion of the shared symmetric key, it's G to the B mod P, the server will sign that portion of the symmetric key using their private key, and the client can verify that signature using the certificate that they verified with the CA. And then they have the symmetric key, and they can encrypt their traffic, encrypting and decrypting with that shared symmetric key. So the whole process, generating a public-private key pair, talking about RSA, going to a certificate authority, having it sign our public key, that certificate authority going to a root CA, having it sign and verify the CA's public key, having root CA certs installed on all of our devices through a process that's assumed to be secure when we install our operating system and or our browsers, that entire process is to sign one thing as one step of generating a shared symmetric key. We don't even use public key encryption for encrypting on the internet. We use it to sign one thing. This is our current application of public key encryption and certs and everything. We sign one value. That's it. Which we like it that way because RSA and any public key crypto scheme, it's slow. AES is fast. But there's some other things we get from this. And then we actually encrypt using the symmetric key using AES. These days, it's AES anyway. Might be different in the future. So that's the only time we actually used all of that public key encryption, certificate authority, all of that stuff. Used one time to sign one value and no encryption. Crazy we do all that just for one thing. But that gives us a lot. That lets the client verify that they are actually talking to the legitimate server when they get that part of the symmetric encryption key. Bless you. So there's another real big benefit that we get. Yes, we get speed, but we also get something called forward secrecy. Even if an attacker, I want to make this one point without talking over music. Even if the client intercepts all of the encrypted traffic that you have with the server, and then later recovers the server's private encryption key, they still can't decrypt anything